So in this video, we're going to talk about 1D optimization examples. Just as a review, when we talk about optimization, we can refer to finding the minimum of the function or maximum of the function. Of course, before you start a problem, this is specified. The optimization techniques are generic, that if you know how a procedure to find the minimum of a function, you can easily find its maximum as well by taking the negative of the function. Right? And the first point that we want to make is that optimization and root finding are closely related. That is because, as we know from calculus, we can define the minimum of a function or maximum of the function by finding the points where the first derivative crosses zero. Right? Here is one such point, here is another such point. We also can remember from calculus that we have the second derivative test that we can use to help us tell whether the point that we found was a maximum or a minimum. In this case, if the second derivative is positive, we have a minimum. If the second derivative is negative, we have a maximum of the function. Right? So instead of finding the roots of the function itself, if we have an algorithm that finds the roots of the derivative of the function, as we explained in the previous video, then we are ready to go and find the minimum or the maximum of the function as well. So we're going to cover some of this in this video. Before we go on to that, I thought to clarify a few definitions. There's a difference between what we call a local optimum versus a global optimum. And so if we have a function of one independent variable here, let's call this one independent variable x, and here we may have y equals f of x, right? And let's say we have a function that looks something like this. Then we can talk about different kinds of maximum or minimum. This point, for example, here, which corresponds to this point in the independent variable, this is what we call a local minimum. This is to differentiate from a global minimum, right? A local minimum is one where locally, perhaps within a small region, there is no other point in the same function that is lower than that. That's what we call a local minimum. This is in contrast to a global minimum, which in this case would be more or less around this point here. This would be the equivalent, the coordinate in the independent variable. This is what we call a global of this function, because there is no other point anywhere in the independent axis which produces a function value which is lower than this global minimum. And by the way, here you would have a local maximum. So let's look at a quick example here. We have a plot, and here's the plot of a function, which the function here is defined as x minus 3 to the fourth plus x. If we take the first derivative of this function, we have it here. And remember, our job here is to find where this point crosses 0. So we set this to 0. Once we have this function here, we can simply apply the root finding algorithms that we talked about in the previous video on f prime as opposed to f. That is, for example, for the Newton method, that which we saw earlier on, instead of using this formula, we replace every time we see f here, we replace it by f prime. So consequently, in the denominator here, you will see an f double prime, and this will be the same idea, the same Newton's method applied to finding the function minimum as opposed to a root finding. Right? Of course, in this case, we don't know whether the function has a minimum or maximum. In this case, we do, because we can look at the plot here, right? We can see actually this is a minimum. In general, unless you plot it, you may not be able to know this. And the same caveats, the same pluses and minuses with the Newton method, as we discussed in the previous video, apply here. right? Meaning that if you start this iterative procedure at a point that is close enough, perhaps around this neighborhood, you will be fine, right? Meaning the method will converge perhaps very fast. But if you start this iteration at some point far away, it may not converge at all, may diverge in fact, and so on. So the same caveats apply here, right? We can also apply the same kind of technique of the golden section method that was covered elsewhere to finding the minimum or the maximum of the function iteratively. And the benefit of doing this is that in this case you will not need the first derivative of the function values itself. In this example here, we're going to look at this algorithm applied to finding the maximum of the function. Perhaps a good quiz or exam question would be to modify the algorithm to apply the minimum, right? So let's suppose we have a function here. We have f of x. X is in the independent variable as usual. And let's suppose that somehow either we're given or we estimated some initial value, which we call xl for lower bound and xu for upper bound. And let's imagine that we are given the knowledge at the beginning that the maximum of this function happens somewhere in between xl and xu. We can then apply a similar idea to the golden section and the bisection method that were covered elsewhere here with some trivial modification. So again, we start by knowing xl and xu, and then iteratively we compute these points x1 and x2, which for the golden section, which I won't go into special reasoning here, but are given by a particular formula here, right? So you have all you need to compute x1 and x2 are the values of xl and xu, which you are given from the beginning, or you find a way to estimate it through some kind of method. You compute x1 and x2, and then you test which one is higher, right? So for example, if x1 is greater than f2, right, then we would take the new xl to be these 2 points, right? Of course, in the way that I have drawn here, this function, it's the opposite, right? We have the situation where this is the case, so we actually take this point and this point to be our new xl and xu, right? And then once we have a new xl and new xu, we simply go back to the beginning, go back here and redo this iteration. So, and we keep repeating until some error is smaller than some pre-specified tolerance, right? So for example, if you're content to finding the accuracy of the maximum of this function up to say 2 decimal places, well, as soon as this interval that we're talking about, xl, xu, gets to something below half of 2 decimal places, you may encourage yourself to stop. So, you know, for example, in the golden section method, you may choose to have this as an approximate error for that procedure. Although that's not necessarily the most universal way to do it. You can simply take the interval itself, and that's a fine enough approximation as well in many cases. So let's look at a quick example here. We have a function, and the function we somehow determined that xl is 0, xu is 4, right? So we start here, and 4, that's our initial interval, and somehow we're given the knowledge that the maximum of this function lies somewhere in between. So what we do is we apply those formulas for x1 and x2, right? And we compute x1 and x2. Of course, once we know x1, we can plug it into f, which is given here, and obtain f of x1, f of x2. And then we can do that test. Is f1 greater than f2? And if so, then we can we apply is f1 is greater than f2. If so, then we can take, which we should do is this particular interval for our new values, right? Which is what exactly we do here. We set this to be that, right? So that got translated to here, and we repeat. We compute f of x1 and f of x1 and x2 and f of x1 and f of x2, and we do the same test again, right? If it's f of x2 here, in this case, f of x1 is still the same, lower. So once again, we update the interval accordingly, and we keep moving along with these ideas, right? So x2 here got brought down here, and we still have x up like that. So we keep repeating until some condition on our estimate for xl or xu, perhaps we choose the estimate to be somewhere in the middle, right? Until this interval gets small enough, and we may allow ourselves to stop this procedure. So here are the key points of this quick video. The golden section, in Newton's method, we can find a maximum or minimum. The golden section, as I described in this video, was for maximum only. You can adapt the method that was described here for a minimum as well, right? Newton's method that we covered before, you really need only one starting point, right? You would like to have the starting point to be close enough to the actual minimum or maximum, depending on what you're trying to find, because if it's not, then it can diverge. In contrast, the golden section method really only requires a bracket, right? Meaning xl and xu, and if you have that and you have the certainty that the maximum of the function is indeed between xl and xu, then the method will converge. There is no debate about that. The other plus, sometimes it's a big plus, is that no derivatives are needed to apply the golden section method here, right? In contrast with Newton's method, you must be able to evaluate the first derivative and the second derivative, as we saw. The downside of the golden section method is that it does converge, but it can converge pretty slowly, right? Newton's method, the convergence is the fastest, one of the fastest known, although it's not guaranteed that we'll find a local or global optimum. Sometimes it can diverge.